Hello there. Welcome to our first remote online graph theory lecture. Um, I'm going to play around with doing this with just some screencasting and not a lot of camera on me because I think that this is a better lighting than the whiteboard I have available at home. But as we start doing these, certainly give me feedback about ways I can make these videos better, but also have some compassion that, well, first of all, I don't make videos for a living, and second of all, I'm just kind of trying to cobble together the best thing I can do here. But I think I'm kind of happy with this. Um, so I'm going to try to keep these things a little bit shorter and more focused than what I would do in an hour-long class. But to start us off here, this chapter 4 has some topics about distance and connectivity. In the first section, distance in graphs, I want to show you some ideas from. So here, and I'll start a lot of these lectures like this with an outline. So this is kind of what I want to accomplish with you guys in the next few minutes is recall what we mean by distance in a graph. We've already talked about distance, but then some technical notions. I want to tell you what I mean by the eccentricity of a vertex in a graph, and vertices may be eccentric to each other or not. And then kind of 4 terms that I want to get out on the table here today. In a follow-up lecture, we'll look at some applications of when these things come up, but the purpose of today is just to kind of get these things defined and work through a specific example, giving you some experience in what it's like to compute these things. So they're called radius, center, diameter, and periphery. Okay, so to get started, sorry, you're going to see a quick screenshot while I wake up my tablet here. There we go. Let's talk about some of these things. So here I've drawn a graph. G, it's a connected graph. I didn't count its order or its size, but you can if you like. And what I want to do is just recall here for you guys what I mean by distance. The distance in a graph. What do we mean by it? Well, it's the distance between any 2 vertices. We denote it like this. Yeah, so you just read that as distance from U to V. And of course, you can write distance from V to U. It's going to be the same. But the main idea is that it's the length of the, and I underlined it to emphasize, the shortest path from U to V. All right. So when we're talking about the distance between 2 vertices in a graph, we don't just mean the length of any path. That wouldn't well define the distance, but it has to be of all the paths between U and V. We have a connected graph, so we know there's at least one such path. Of all the paths between U and V, we take the shortest one. Okay, that's what we mean by the distance. Let's look in our example here. I've kind of pre-drawn a lot of stuff here, so this slide is going to look a little bit busy, but let me just sort of annotate it for you as we go. What I've done is I labeled 2 vertices in this graph, U and V. Can you see them there? I drew 2 paths from U to V. One of them is drawn in red. It has length 1, 2, 3, 4, 5. The other one I drew in blue. It's an alternate path. It has length 6. But the distance from U to V isn't 6, it's 5. I'm always going to choose the shortest path. And you can pause the video for a second if you want to and convince yourself there's no shorter path from U to V than 5 vertices. Okay, so that's what we mean by distance. What else have I done in this busy picture? Well, above each vertex, I wrote a number in red. And what that number is, it's the distance from U to the vertex. Right, so like just looking at these things, the distance from U to U is 0. This guy is adjacent to U, its distance is 1, so on, distance 2. Both of these vertices are distance 3. Okay, so I did that for every vertex. Maybe you want to stop the video for a second and check my math. But I claim that those red numbers are the distances. All right, so let's use this picture to define some lingo here. First up is this idea, eccentricity. Eccentricity of a vertex U. The notation for it in the book is just this, E of U, eccentricity, and it's the maximum of all those distances. All right, so in our example, what do we got to do? We got to look at all those red numbers and choose the biggest one. To me, it looks like the biggest one is 10. Looks like the vertex W is 10 units away from V. So by the way, maybe I'll try to make some room up here. That vertex W, there's some language that we would use to describe that. It's eccentric to V. The vertex W is eccentric to V. I'll write it down a little bit here. Let's keep looking at these definitions. So eccentric to just means furthest possible distance away from. Okay, what else we got here? The radius. The radius of a graph is just the minimum of all the eccentricities over all the vertices. We can't see those in this picture. We're only looking at the distances from U. The center of a graph is the set of vertices whose eccentricities are that minimum. They are the radius. Okay, these are sort of dual notions. The diameter of a graph is the maximum of all the eccentricities, and the periphery is the vertex set in which the eccentricities equal that diameter. So roughly speaking, the center of the graph is the set of vertices whose eccentricities are as small as possible, and the periphery of the graph is the set of vertices whose eccentricities are as big as possible. I think it's important to note when you're thinking about this stuff that radius and diameter are numbers. Center and peripheries are sets of vertices related to those numbers. Let's go back to our example. Taking that same graph, stripped away the measurements from the vertex U, but we said that E of U was 10, the eccentricity of U is 10, and that vertex W over here was 10 units away from it. Its distance was 10. So here I've written it. We'll say that W is eccentric to U. Okay, I think this is actually kind of interesting, but maybe take a second. U is not eccentric to W, right? U is not a vertex that is as far away from W in this graph as you can be. There's a vertex up here, I labeled it X. That vertex X, if you count, is 11 units away from W. 11 is bigger than 10. So this concept of eccentric to isn't symmetric. It kind of makes sense. I mean, in this example, just because W is as far away from U as possible, it doesn't mean there aren't things that are further away from W. It just means that any such thing is closer to U. Yeah, you can look at the picture. All right, so here's a little exercise for you that you can stop and do before I scroll up. I'm talking about this exercise down here. Label every vertex with its eccentricity. Like we've already calculated it for U, so I would label the vertex U with 10. So maybe stop for a second and see if you can do it. What you're trying to do, let's look at this neighbor of U. You're trying to write down all of the distances from that vertex to every other vertex in the graph, and then pick the biggest one. The biggest one is the eccentricity. All right, so you can work for a second, and when you're ready, turn the video back on and see if you agree with me. So here, this time writing in black, I have written the eccentricity of every vertex. I didn't give every vertex a name, but I've written the eccentricity of every vertex. All right, so like we said, the eccentricity of the vertex U is 10. This guy here, you can check it. W is 9 units away from it, and nothing is further. W and actually X are still, just W is 8 units away from this vertex, nothing is further, and so on. So that's what I've done across every graph. There's lots of patterns. We're going to have conversations about this. I hope your brain is thinking of all kinds of questions as you look at this graph. But here, let's just make sure that we have digested these definitions. So looking at that graph, what is the radius? All right, you can pause and scroll back up if you want to, but remember that the radius is the minimum of all the eccentricities. So I have to look at that graph and pick the smallest of all of the eccentricities. I think it's 6. I think it looks like the radius of that graph is 6. What's the center? The center of that graph is the set of all those vertices that have eccentricity equal to the radius. And I'm just going to kind of indicate, I'm not going to name those vertices. I'm going to just sort of schematically do this by drawing a couple of black dots down there, or blue dots, excuse me, these vertices right here that I've colored blue in the graph. They're in the center, they're central vertices. What about the diameter? Diameter is just the biggest eccentricity. Looks like it's 11. The diameter of that graph is 11. What's the periphery? The periphery is the set of points that have eccentricity equal to the diameter. It looks like there's 2 of those. Yeah, in fact, they even have names. I could use them, X and W. Those vertices are in the periphery of the graph. Cool. Well, so that's kind of it for this thing. I wanted to get across those 4 notions. 4 notions: radius, center, diameter, periphery. We'll end with just one more little piece of lingo here. 2 vertices, let me kind of scroll back up so you can see them while we're talking about it. 2 vertices whose distance apart in the graph is the diameter are called antipodes or antipodal. They're sort of as far apart as you can be. And here's a little something that you can think about, and we can talk about it or bring it up next time. Maybe it'll show up in a homework assignment. But for a connected graph, you have to have a pair of antipodal vertices, and those, at least one pair. There might be more. We have exactly one pair in our example, X and W. And those vertices will always be mutually eccentric. So what do I mean by that? I mean, if you look at this graph, the distance from W to X is 11, and the distance from X to W is also 11. And I guess that's not really enough to say that would always be true, that those distances are 11 and there are no bigger distances. So if X is furthest away from W, W being its antipode, then W will also be furthest away from X. Okay. So what are we going to do next time? Well, we're going to look at some properties of eccentricity. In particular, we're going to look at some of these properties of how they manifest in the subclass of graphs that are trees. And then I think I want to leave with just kind of a hint as to what kind of example that I have in mind in thinking about it. And you can think about this too, but what I have in mind is thinking about the graph that is sort of acquaintances. So let's just sort of end with kind of jotting an idea down here, something to think about. What if we look at the acquaintance graph? The acquaintance graph where nodes represent people and edges are indicating whether the person is acquainted with each other. Acquainted with, maybe they're friends, maybe they work together, maybe they've appeared in the same movie. I don't know. There's all kinds of ways that people can be acquainted or not. Let's stick with maybe movies. So each one of these nodes represents, say, an actor or an actress, and I'm drawing an edge between them if they have appeared in the same movie or not. So the question I kind of want to leave you with is like, well, what do these notions of like distance and radius and center and periphery, how do you interpret them in that context in this graph? All right, maybe you've talked about a problem similar to that. Okay, so we're going to stop this for now. Yeah.